Hello and welcome back to another fracas of Friday Physics with Mr. Francois. Today we're going to be talking about how to solve a 3/4 problem using a 3-variable chart. And the way that we do that is that we take a chart like what you see right here, and what we do is, instead of doing the normal x and y for our horizontal and our vertical, we split our y values up into up and down. And so I'm going to move this off to the side here so that we can get started on the problem that you see before you. Now, if you so choose, you may wish to pause the video at this point so that you may try to solve this problem on your own, and then come back and see if you've gotten the correct answer and done everything according to how it should be done, or at least, I hope, at least as far as how I do it. So, pause the video and try it out, or follow along right now. So, green arrow, bull-wielding superhero fires an arrow from 20-meter high building with a velocity of 30 meters per second at a 35-degree angle above the horizontal. It strikes a robber on the second level store of a mall 5 meters above the ground. Horizontally, how far away from the store was green arrow? Okay, so what we are looking for in this instance is the x displacement. Now let's see what values we actually have. Now I know right here it says 20 meters, but that is not a value that we want to use because that is a height. It is not a displacement, which is what we use in our chart and in our equations. Now what we want to use, okay, is this velocity right here, the 30 meters at a 35-degree angle above the horizontal. So that's a positive 35-degree angle, not a negative one, which is what it would be if it was below the horizontal. So what we want to do is we want to take that 30 meters per second at a 35-degree angle, and we want to split it up because we cannot use anything that is in both x and y directions. We want to use things that are only in the x or only in the y, and that makes it the easiest so that we can use our special equations from linear motion. Now, so if we put this into a triangle, as I've already shown here, our y value is on the vertical side here, and our x value is the horizontal side. And if we want to find those values, we use the x and y equations that we normally do, which is the magnitude of our vector. In this case, it is 30 meters per second, times, in the x case, cosine of our angle, 35, in order to achieve it. And for the y, it's 30 times the sine of our angle, which is 35. This means that our vi in the x direction happens to be 24.57 approximately. I'll write that in on my chart here. And my VI y is in fact 17.21. Now that goes in the y up because we start our path in the upwards direction, and we put that there. Now, before I go any farther and put in other values, I need to take a look at what's going on as far as known values for this. Now, our accelerations are already known to us. We know our acceleration in the x direction is 0. We know our acceleration in the y direction due to gravity is the negative 9.81, and that's for both our up and down because it doesn't matter whether we're going up or down. Gravity always pulls us down. It's like that really, really bad friend that always just says the very negative comment. Okay, so now we need to address the elephant in the room, and that is, what the heck do we do with y up and y down? So the thing is that our three-pronged chart that we have here relies upon an assumption, and that assumption is that we get all the way up to our maximum height and then we come back down. Now, we can safely assume that to be happening in this problem because, as it says here, that it starts at 20 meters high up and it ends 5 meters above the ground. That means that it's starting from a high point and going to a low point, and we're shooting up originally, which means that we have a positive y value. In order to get to a negative displacement, you eventually have to switch over to a negative y value. So we know that we have an up and a down to this problem. Otherwise, we would have to see whether or not it is possible or not by finding out what the time it would take to get up to our maximum heights would be, and the time that we have in the x direction. And if the time in the x direction was smaller than the time they would take to get to our maximum height, it wouldn't work out. Now, since we know that it does achieve its trip up to its maximum height and then comes back down, we can give it the borderline between our up path and our down path, and that is that it hits the maximum height. At the maximum height, we have stopped going up, which means our final velocity in the up direction is 0. Likewise, seeing as how down takes over at that point, our y initial velocity in the down direction is 0 as well, because it starts going up, it loses all of its original upwards velocity, and then from that point, which is 0, it switches to a negative velocity and heads down. So there are our known values thus far. Now we started at that 20-meter high building, we ended up 5 meters above the ground, so that's a total y displacement of negative 15 meters. Now I cannot put that into my chart because that is not the displacement going up and it's not the displacement going down. The displacement going up is how far up to the maximum height. The displacement going down is how far from the maximum height do we go. So the difference between y up and y down must be negative 15 meters. Or not really the difference, but the addition of our displacements in y up and y down must be negative 15 meters. So we can, however, so there is a relationship between these two values here of y up and y down displacement. So let's solve for that, because if we take a look at our y up column here, we have 3 values, which means we can find out what the displacement is, and that is actually what our maximum height is above the 20-meter high building. So if we want to find out what that is, we use our handy-dandy equation. We know VI, we know VF, we know acceleration, and we want to find delta x. That means we use our equation of VF squared equals VI squared plus 2a delta x. And when we rearrange this in order to solve for delta x, we have delta x is equal to VF squared minus VI squared over 2a. And that would leave us with the correct displacement of 15.10 meters up. So that goes into here, 15.10. Now, as I said before, our delta y up and our delta y down has to end up totaling the negative 15. So seeing as how we already know our delta y up, we can rearrange this in order to get our delta y down. So delta y down must be the negative 15 minus 15.10. So that actually means that our delta y down is in fact negative 30.10 meters. So I can throw that into my chart here. So negative 30.10. And again, now I have 3 values, which allows me to solve for other values. Now, ultimately, we are looking at trying to find the displacement. This chart helps us with finding out other values, such as maximum height, and how long does it take to get to the maximum height, what's your final velocity, things of that nature. Now, what we can do in order to get to our question for this one is that we can find out what our time was here, because our y up and y down, we've split our y direction into parts, not halves, but parts. So that means that if we take our y up time and we add it to our y down time, that should be our total x time, because again, x isn't time is not directional, so therefore the time that we have in the x is equal to the time that we have in the y in total. So we need to find our times on each side, which, now that we have plenty of values in both columns, we are able to find those. So by doing a little bit of math for the y up side, we find our time with the equation of Vf is equal to Vi plus A delta t, which rearranges to Vf minus Vi over A is equal to delta t, which for our y up equals 1.75 seconds. Now, if we go over to our y down, we can use the equation of our delta x is equal to Vi delta t plus 1/2 A delta t squared. And because our Vi is 0, this entire term gets canceled out, because anything times 0 is 0, and adding 0 to anything does nothing. So we end up with delta x is equal to 1/2 A delta t squared. And when we rearrange this to solve for delta t, we end up with delta t is equal to 2 of delta x divided by A inside of a square root. And usually we would put a plus or minus on this. However, there is no such thing as negative time in this case, because there was no time before he actually fired the arrow, of which the arrow was in flight. So we might as well not even consider it. So this actually ends up with a time of 2.48 seconds approximately. So if we take those values and we throw them into our handy-dandy chart of science, projectile motion, and this is 1.47, and this one, our total time in the x direction ends up being the sum of these two, which 1.47 plus 2.48 ends up equaling 3.95. If we take that and we then use it with our handy-dandy chart here, because now that we know enough about the x direction, we can actually solve it. So if we put that into our delta x is equal to Vi delta t equation, that is really the only equation that works for the x direction, our delta x is in fact the 24.57 for our original, and the 3.95 for the time, which gives us a delta x of 97.05. That is a really long shot. Well done. Now, if you've watched the other video that I've put out of the two variable chart, you will notice that the answer here is different than what we got over there. That is because we did plenty more calculations in this one. I mean, you can see all the work that we've done so far. And what we found is values which we then had to round. And every time we round, we add on a little bit more error, a little bit more error, a little bit more error. If you do this, you do accrue a little bit more error. It is not necessarily wrong, it's just not as accurate as it could be. So if you gave me this answer using this method, I would not mark you wrong for it, but you have to be careful. Try to round as little as possible, and my general rule of thumb is never round more or beyond 2 decimal places. So don't round to, say, the ones place, or forbid the 100th place. Try to keep it to as many decimal places as possible. So this has been a good example of a 3-pronged chart. Remember that this is this is not required, but is only works so long as we have a motion up and down, and that you can only use variables from the same side, from the same column, in order to calculate other values for that column. It has been a pleasure, and I will see you in class.